Hi everyone, welcome to our second NLP workshop for RNNs. I'm Jackie and I'm an event lead at ACMAI.
Hey all, I'm Arth. I'm also an event lead at ACMAI.
Yeah, and I'm also an event lead at ACMAI, and I'm Vincent. So if you guys haven't checked in already, we have our code multi-class with $2 signs, and you can check in at acmucsd.com. Yeah. All right. Okay. Cool. So we're gonna have an outline for how we do this notebook. We have a main notebook and an interactive notebook. So we're gonna be coding along with everyone on the interactive notebook, and we'll have the main notebook published after the workshop. So there are 5 points here: setup and exploration. So we're setting up the data and exploring the data, and then pre-processing. So we're turning that data into a format the model likes. And finally, we're building, training, and evaluating that model, and we'll finish off with a conclusion. Yeah, okay, so I guess we just click on this link here. Right. Oh, okay. Yeah, so first thing to do is you want to make a copy of this. Oh, I'm supposed to look at that screen. I think it's more convenient if I look at this one. Yeah, you want to make a copy of this notebook before we start. Did you just make the copy? Okay. Yeah, I guess you just, here we just click a link. Wait, what? Thanks. What do you mean? Oh, shoot. That's the check-in code. Sorry. I'm so sorry. Okay. We have a table of contents, setup and exploration, as previously mentioned, pre-processing. This includes modifying the data, cleaning the data, and then we have modeling the RNN, training, and conclusion. So I'm going to be covering the setup and exploration. Let's just get started here. Yeah, so we use a reference notebook, and this is actually found on Kaggle. Yeah. Yeah. Oh, I mean, if you want, yeah, you can click on that link, or you can just simply, wait, where's it? Oh, check in with this code here at acmucsd.com. I am so confused. What the heck is going on? All right. Does everyone have this check-in code? Yes? What? Oh my God. All right. Okay. I'm so confused up here. Yeah. Anyways, we're gonna move on. This is the interactive notebook. This is the link to it. So does everyone have this link and the check-in code? Yes? Yes? Okay, all right. Yeah, so I'm gonna be covering setup and exploration. Here we're gonna start here. So this link leads to the data set, and this is a Kaggle data set. Yeah, so we're basically downloading the data set with this code snippet. I'm not gonna dive too much into depth on what this code does, but I have the zip file of the data stored on a Google Drive. And this code is basically pulling that data from that drive and putting it in our notebook. Right, so this should only take like a few seconds. So if you're having trouble with downloading this data, we do have like kind of like a backup, and you can click on that link. One, download the data set. I click on this one. No. Okay. Yeah. So you just follow these 3 steps. It's really simple. you just download the data set from Kaggle, and then you can take that zip file on your local machine and drag that into the file directory within this notebook. Yeah, and then we also import our libraries. So we use a few libraries, NumPy and Pandas for manipulating tables, NLTK, that stands for Natural Language Toolkit. It is a Python package for preprocessing text. And we use TensorFlow and Keras for building our model and training it. Yeah, okay, so does everyone have this data? Can I get like a raise of hands? Yeah, does anyone have any problems with this data? Like downloading it, pulling it from the drive? Anyone? No? Okay, all right, cool. So I'm gonna keep moving on. Yeah, so we're basically loading this data set in with pandas, and we're going to explore it. So let's first print the shape. So these are the shapes. Just a small side note. We have, it's a table, so there are rows and columns. The train, test, and validation, they all have a different number of rows. So each row is a comment. And there are 2 columns because there's a comment, and each comment has an emotion associated with it. So this is an emotions data set. We have comments corresponding to emotions. And in this case, we only have 6 emotions. So I want to ask everyone here, what's the difference between like train, test, and validation? So why do we split up the data like this? Anyone? Anyone? Right. So, okay. So for short, we split up the data because 1, we want to train the model. That's the train set. And 2, we want to validate the model to check up on how good it's performing. And 3, we want to eventually test our model. We want to put it into the wild and see just how well it does. All right. Okay, so here we're going to take a look at train data. Yeah, so you can see it is a data frame, or just a simple table. So we have 2 columns, comments and emotions. There are 6 different types of emotions, and we have 16,000 rows in our train data set. So what do you all notice about our data set? Anyone? All right, okay, I guess I'm gonna continue talking. So yeah, we have comments, and these comments, they're pretty much in English. They look fine. They do have punctuation, capitalization, and they do have, I'm gonna assume they might have some slang. Right, so we wanna print out all the emotions, right? All the emotions in our data set. We have sadness, anger, love, surprise, fear, and joy. So what is multi-class classification? Does anyone know the answer to that? Yes?
I guess in contrast to binary classification, it's just when there's more than 2 classes associated.
Yeah. It's a really simple idea. So let's start with binary classification. So if your model is supposed to predict whether something is good or bad, that's binary. But in this case, it's multi-class because there are 6 emotions instead of, let's say, 2. Right, okay. And pre-processing, I think Jackie will take over.
Okay, so first we'll be doing some data set modifications. So we'll be adding a column names link to the trained data, and this will be helpful later. And then we're going to be replacing the emotion names with integers. So all these emotions will be replaced with integers 0 through 5, and we're going to be using sklearn's label encoder class to do this. So we have our first to-do, which is basically the interactive part of this notebook, where I'll be using the label encoder with you. So it's pretty simple. We just need to type label encoder, just calling that function. So that's the only to-do we have for this. And make sure to run it after you have coded that. Okay, so now let's take a look at the modified trained data table. So this is what happens after you run that code. The emotions are labeled from 0 through 5, and it also says the length of each of the comments. Make sure you run all the cells. Okay, so now let's do some data cleaning. Does anyone know what cleaning the data means? It basically means changing the data into a format that is more acceptable for the model. So the first thing we do is take out stop words. Stop words are words commonly used by humans that don't really give much meaning. So for example, in these examples, well, hold on. Wait. Sorry, this cursor. Okay, so words like and is and for doing all that aren't really helpful for the model. They don't give much meaning to the sentences, so we can change this sentence to just these words and this sentence to just these words. So we're going to keep using NLTK. So this will be taking the stop words out of these example sentences. Okay, so we're going to be downloading this NLTK. So okay, so that's the only to do. So after that, press the play button to run the cell. Okay, so as you can see, this basically took out the stop words from these sentences, just like the example we had above. So moving on to stemming. Stemming is basically when you're taking the suffixes and prefixes out of these sentences and just reducing it to you can reduce it to lowercase and reduce it to singular instead of plural. So these are the examples. So for example, he is running and jumping. We can change that to he is run and jump. So let's do the same thing from stop words, but instead we're going to be using the Porter stemmer to handle the stemming. Okay, so after that, make sure you run the cell. So you can see that these sentences were reduced using the stemming. So the last thing I'll cover for preprocessing is one-hot encoding. So this is not a traditional one-hot. This is basically just using Keras' own function for that. So we're basically hashing the words. So we're assigning the words to a number, and this number is randomly generated. And our vocab size will be preset. So these words are assigned a number from 1 to 10. And we also have padding, which is basically if the sentence is shorter than like the longest sentence, then we're going to add some zeros for padding for that. So let's test this Keras' one-hot function. Okay, so there's a to-do right here. So we're going to be doing one-hot. So we're going to say our input text is the sentence that we have above, and then we're going to say n equals 20. Okay, so run that cell. And that's going to be assigning a number to each of the words, and this also preserves the sequence of the words. So we're going to be using everything I just talked about above into our text cleaning function. So this entire function is too complicated to explain, but you can see that we use the stop words, or we call the stop words and stemmer functions, and then we use one hot here as well. So basically this whole function will be pre-processing the data. So we're going to apply that to our xtrain, xval, and xtest, so our train validation and test data. So make sure you run those cells. Okay, so now we're going to be creating, or we're going to be using a more traditional one hot for the Y values, which are basically the emotion labels. So you can run this. And so this is a graphical model of the traditional one hot approach. And we're going to print out the shape of the Y values. Okay, so after this point, we have pre-processed all of our data and we're ready to start modeling. So Arthur will be taking over the modeling part.
All right, great. So far, we've set up our data by downloading it. We've explored our data. We know that we have to do a multi-class classification problem. And we've pre-processed all our data so that our computer can actually understand and look at all of the data in a way a computer can. So now we want to look at a model, and we want to pick a model that will best work with our data. So let's look at this image of a standard neural network. So a standard neural network, also known as a forward pass neural network, works by having an input layer. That input layer gets some data passed to it, in our case sentences. It passes through that hidden layer, does some backpropagation, and then you end up with an output layer. If we were to condense this drawing, we have generally our inputs, our hidden layers, and our outputs. Now, one issue here is that if a general forward pass neural network looks at a sentence, for example, it will take one word, run it through the model, and then throw it away. Take the next word, run it through the model, throw it away, and so on and so forth. So basically, it doesn't remember any previous words, which is a problem because in sentences, the meaning of a word depends on the context of that word. This is what's known as sequential data. Sequential data is a data set where each data point relies on previous data points. So we want to create a model that will work with sequential data like sentences. This is called a recurrent neural network. It's a special type of neural network that's built to process sequential data, and it has what's sort of called a memory. So let's look at this image of a simple recurrent neural network. So recall that a forward pass network just goes from one to the next. A recurrent neural network will take the first data point, that's input 1, pass it through the hidden layer, and then that'll have some output. That's just for the first word. But for the second word, it will take the data of the second word as well as some data from the hidden layers of the first word. And then that will condense into the output for the second word. And this will keep happening for every single word in every single part of the sentence. So another way to think of it is it'll look at the first word and it'll remember it. Second word, it'll remember it, so on and so forth. And by the time you get to the 10th word in a sentence, it'll have the knowledge of all previous 9 words. In other words, it can remember the entire sentence as it learns, and it can remember, most importantly, context. So RNNs are generally great for NLP purposes because they can remember the context of previous words. All right, so we've talked about RNNs at a pretty high level, but let's talk about actually building an RNN. So building an RNN using TensorFlow, we're going to be using a couple different layers. The first layer here is called an embedding layer. Now, embedding layers, they will take our giant data set and convert that to a smaller latent space. So let's go ahead and code that in. So we call embedding, which is a function from TensorFlow. We have our input dimension, which is equal to our vocab size. I believe that was like 11,000. We have our input length, which is the maximum length of a sentence. I believe this is the longest sentence that we had in our data set, which was like 300 words. And then finally, we have our output dimension. This output dimension is fairly arbitrary. We're picking 150 because that seems to work well with this model. So what this is doing, it's taking the input dimensions of our massive representation that we coded before in preprocessing, and then it's trying to put it to a smaller latent space that can be easier for the model to process. We then have what's known as a dropout layer. Now, neural networks, as you might know, are pretty prone to what's called overfitting. Dropout layers will have a parameter, and that parameter has a certain probability of just dropping a neuron, and that helps prevent overfitting. In this case, we have a probability of 0.2. Okay. Next up, we'll add our simple RNN. So the simple RNN is basically what we have in our model here. So we'll call the simple RNN function, RNN 128. And that'll basically be doing most of the processing for our data. We have another dropout layer, a dense layer. A dense layer is basically, sorry, I'm not sure what's up with the screen, but are you guys able to get all this down? I guess. I think it's overheating a bit. I don't know. In any case, a dense layer, basically it takes some input and then it puts out a tensor of certain size. So we have a sigmoid layer. This one is normally used for binary classification. Don't worry about it too much. We're adding it to our model. If you don't have to, you can. But what's more important is a final dense softmax layer. So we'll type that in and I'll explain what that means. 6 activation equals softmax. All right. So softmax, you can learn more about it at this link right here. Basically, it's a function that will take some number of classes and it'll output confidence values for each of those classes. In our case, we have our 6 emotions. So whichever emotion has the highest confidence value will end up being the correct emotion. All right, we go ahead and compile it. We're going to use an atom optimizer. Categorical cross entropy is a loss that's good for multi-class classification. And then we're going to be using accuracy, precision, and recall. So if you go ahead and run that, we have a function. Now, normally we go over this training, but the thing is we're building a whole neural network model, and that can take a little bit of time. In this case, each epoch takes about a minute. So we did pre-train a model right here. I'll talk about what all the inputs are, and then we'll talk about the analysis. If you guys want to run it on your own, it should take about 10 minutes to run after this workshop. OK, so we're going to go ahead and fit our model to our data using this fit function. So we put in our X-train data and our Y-train, which we created before. And now we're going to specify the number of epochs and the batch size. So in one epoch, the model will look over the data set one time. And in each epoch, it'll learn something new. And for a batch size, that's basically how big each chunk that the data set looks at is. In our case, we're going to be saying our batch size is 64, so it'll be looking at the whole data set 64 elements at a time. We put in our validation data, and then we run it. So this is what ran over the course of 10 minutes. You can see our accuracy increased over time, and our validation accuracy also increased over time. If you go ahead and run this final cell after you after you train your model, we'll run it on the validation and test data. So on the validation data, we see we have an accuracy of about 82% with precision and recall following suit. And then on our test data, which is the real test, we have an accuracy of about 81% with precision and recall following suit. Now, this is pretty good, 80% for a model with only 10 epochs, but there are a couple things we can do to improve our model in the future. So first of all, we can use different preprocessing techniques. We talked about stop words, stemming, and one-hot encoding, but there's plenty of other things, lemmatization, et cetera, that we aren't able to cover in this workshop. We can use a different RNN model. So as you guys remember, we used the simple RNN, which is a simple RNN. RNNs come in multiple different shapes, sizes, flavors, and you can pick the RNN that works best for your problem. And finally, we can train for longer or differently. So if you recall, we only did 10 epochs with a batch size of 64. If you increase the number of epochs, you'll look at the data set more often. And if you decrease the batch size, it'll take longer to train, but since you're looking at less data at any given point in time, you can look at that data with more scrutiny and thus train better. But yeah, this is generally an overview of using RNNs for NLP. So if you guys want to go ahead and use this data set, or sorry, this workshop notebook at home, we have a main notebook. This main notebook basically has everything we ran. It has our pre-trained data set, et cetera. So if you want to fill in some code that you might have missed, the interactive notebook's also available. And finally, we have a summary graphic, which goes over everything we talked about, from preprocessing to the neural network. Yeah, that'll be it for our workshop. Thank you guys for attending. Do you guys have any questions before we distribute food, or no? Yes. Oh, for sure, yeah. You can take a picture if you guys want. Any other questions about content, or is that good? Yes. For sure, yeah. Does everybody have pictures and stuff? Looks like it. Okay, are you talking about the pre-processing one-hot encoding? Yeah, we can do that. Okay, so we'll scroll all the way up here. Yeah, do you want me to review it, or do you want to just look at the code? Sure, yeah. So just to review the code, we have 3 sentences. These are just example sentences to kind of show you how it works. We get the max len of the sentences. In this case, I think this sentence has the longest length. And then we go ahead and encode each sentence. So we use this function one-hot with an input, and then a vocab size of 20. That's just arbitrary. It's just to make sure that we have enough space for our hashing. And then we go ahead and compare to our original sentence. So here it looks like Caleb is 13, 8 is 19, sum is 16, donuts is 19. And you can see that kind of follows suit here. Does that make sense?
Yeah, what are the trade-offs of like increasing or decreasing n?
Yeah, so if you're familiar with hashing, this specific function uses hashing to be able to get the values for each word. But let's say you have a smaller n, a smaller vocab size, then you might get some collisions in your hashing. What that would mean is like Caleb and 8 might have the same value, which is bad because then our model will think that it's using the same word twice. So you want to have an n that's big enough for the model to have its own hashing, but for each word, but not so big that it slows everything down. Cool. Any other questions? All right, great. I'll leave this slide up, and we can go ahead and get some pizza out. Sorry, I just realized there were some questions in Twitch chat, so I'll go over those real quick. One question was, so your model doesn't memorize the data. Well, so for RNNs, it doesn't memorize every single sentence. That's why we're using, oh, was that for explaining tests, validation, and training? Yeah, that's why we have the split. Can you explain how the embedding function maps vector into latent space? So TensorFlow has a lot of abstractions of this sort of stuff. Effectively, what you need to know is that the embedding function will take that and then map it to a smaller latent space. There are some complicated diagrams on that you can search up online. I believe TensorFlow has some documentation on embedding, but that's essentially what it does. Sorry if that explanation wasn't super detailed. But yeah, all right, let's go and distribute pizza.
Thank you, Twitch people. We'll be ending the stream right now. Thanks so much for coming.